afternoon, everybody. Thank you again for attending this set of CASS talks. But today we are here to listen to Professor Omar Paranaiba and to know how we can do future computers without no electric current. So a very exciting subject. So Omar Paranaiba receives his undergrad degree in computer engineering and also the master engineering degree and the PhD degree in electrical engineering from Pontifícia Católica in Rio de Janeiro, in Brazil. Since 2010, he is a professor at the Department of Computer Science at the Federal University of Minas Gerais, Brazil, one of the top Brazilian universities. So his main research interests involve emerging nanotechnologies, nanocomputing, and computational nanotechnology. Omar is head of the Nanocomputing and Computational Nanotechnology Laboratory at the Federal University of Minas Gerais. And Omar is also a member of several conference committees and associate researcher of the Brazilian National Research Council, and author and co-author of more than 90 publications in scientific journals and conferences. And he's also the head of the special interest group on integrated circuit design of the Brazilian Computer Society. So thank you very much, Omar, to accept our invitation to give this talk today in this very exciting subject. So now I will give you the control of the presentation to start your screen sharing. So you have already the control. So you can now do your screen sharing to start your presentation.
Okay. Thank you, Ricardo.
Just an observation. I also would like to ask again to all attendees to put their names, institution, and where you are now, because we would like to know where is the attendance of each talk. So thank you very much. So Omar, the floor is with you. Thank you.
Thank you, Ricardo. It's not necessarily a floor now, but the screen is mine now. And can you see my screen now? It's okay? Yeah, I think it's okay.
It's okay. It's perfect. Thank you.
Okay, so thanks again, Ricardo. And before I start my talk, I would like to congratulate Ricardo for one more initiative. Ricardo has done a very good work to spread to our scientific community all the research that we have done here in Brazil, and also open opportunities for the Brazilians when he invites a lot of very important guys to give their talk here in Brazil. So we start with my talk today. The idea here is to think far, to think in the computer in the medium to far future. So let's think about the future of computers, and the idea here today is to give up from the traditional. So I would like to subscribe here the no electric current computers. And what's the main advantages of these computers, or these future computers, are low energy machines. So here's the agenda of this talk. I will first introduce my laboratory here in UFMG. And later I will talk about computing, device miniaturization, and finally speak about nanocomputing and these machines with no electric current. So let's start with the laboratory, the Nanocomp lab. What we have done in the lab is the research interaction between two very different research areas: computing, computer science, and nanotechnology, nanoscience and nanotechnology. So we do this in the two different ways. So we apply some computing, some algorithms, and some software development to help the people in the nanoscience and nanotechnology area. And as the main topic of this talk today, we also apply nanoscience and nanotechnology in order to think in future computing systems. And this is a cycle, because if we apply computing to help to develop nanotechnology, we can improve nanotechnology to create the new generation of better computers, and then we can do better with nanotechnology, and then we can do better with computing. This is the cycle that we try to do here in the lab. So before I talk about the nanocomputing, which is the application of nanotechnology in computing, just a little view about what we have done with computational nanotechnology, the other side of the coin. I have a background I also have a background in artificial intelligence, and we have applied it on nanoscience. Sorry, I left this one here in Portuguese, but you can understand if you don't read Portuguese. It's quite the same. So just one example, we have a book. I have written a book that was published some years ago, and we have done a lot of work here. Maybe the main work today, we have a very big project we call NG Graphene. Here it's a picture of our plant, our product plant. So the idea here is to turn the graphite. Minas Gerais have one of the biggest graphite mine in the world. So in order to aggregate value to this graphite, we are turning this graphite into graphene and searching for applications. So we have a very huge project here, over 5 million reais, over 5 people working here in this project, and we apply some machine learning and optimization in order to improve the quality and the development of graphenes, such as in this work that was published early in this year. So let's to the topic of the talk today. So before I start to talk about nanocomputing, let's do a highlight about the computer, the evolution of computer. So the first thing, what is a computer? I think everyone knows, at least you that are listening and watching to this presentation. A computer, it's simply, in the simplest definition, a machine to automate calculations, right? What we want to do is calculation. And we want a machine that automates this calculation to do a lot of calculations in a single fraction of time. So if you look for the computer prehistory, we can say that the abacus was the first computer, because it was a machine to automate the computation. But it was a mechanical one, and very limited one. Also, the engineer rules is also another good example of a mechanical one. Here we turn to electronic computers. These are some women that work in the development of the ENIAC, the first electronic computer ever. It was a little bit over than 70 years ago. And it was a building. It was a building for one computer. So it's very strange for us today, because you usually use a computer in the pocket. And then we had the transistors. So here it's a picture of the first transistor that gave the Nobel Prize for the for the inventors. And it is a very strange structure, but it's like the source, the drain, and the gate. And it's a switch that controls the electronic current. In the present, the computers are quite different. This is the main picture of a computer today, but it's quite difficult to find a guy today that really uses a desktop, sometimes to games and something like that. But normally we use more computers like that, more simple and easy to carry. More simple computers, like a tablet or a smartphone. It's the main, I think it's the main computer machine that you use today. So we carry the computer on the pocket. And one of the problems here is that it consumes a lot of energy and electrical current. So as we carry with a battery, our battery does not go for much. So in less than 1 day, you have to recharge the battery again. But we still have builds of computer, but now not a build for one computer, but we have builds for millions of computers at the same site. And this is very useful because many of the things that we do here in the cell phone actually are processed in this cloud computer, as we know. So when someone wants to work with computer, the first thing that come in mind and the first thing that give the attraction to work with computer is application. So someone has worked with, has played a game or has used an app, and he start to deserve to learn more about computers. But we have to remember that there is, to the application to run, you have physics behind it. So you have a very big gap between the physics that it's really happening to computer to work and the application on the top of the layer. But fortunately, you have a lot of abstraction levels between the application and the physics. So the computer scientist does not need to know about the physics behind the computer. Maybe he just has a small knowledge about what happened, but he does need to have control about it. And the simple thing that happens to the computers to work is the control of the electric current. So what we have here in the top of the physics is the transistors, our device, that are switches that allow the electrical current to go on or off. This is the basic for a computer. That's what we are going to try to do different in this talk today. So let's talk about the device miniaturization. We know that the computers have changed along the years and changed a lot. And how it changed? First, we are now talking about electronic computers, right? So the first electronic computers, they didn't even use transistors because the transistors were not invented physically at that time. So for example, the ENIAC in the 1940s used vacuum tubes. And these were the switch that allowed the control of the electrical current. Just 1 year, later, the ENIAC was ready to run. The first transistor was released in 1947. And since then, as I said before, you used to have buildings to fit a computer. The computer can fit in a chip. And this is a very old computer. It's not a very new one. This is a very, very old. But it was already inside a chip. Why it happened? It happened thanks to Moore's law. I think everyone from the audience know what is Moore's law. But the Moore's law, it was given, it's a sentence given by, it was in a paper in the 70s by Gordon Moore. And he said that the number of transistors in a dense integrated circuit could double approximately every 2 years. And we have seen it since then. So the transistors shrink, and we have more transistors in the same area since then. Today we are facing some challenges with the Moore law. There is a very funny joke nowadays that say that the number of people that say that Moore's law is ending double approximately every 2 years. It's a very nice joke for us who works with it. Just some years later, in the next decade, Dennard observed that the voltage and the current of the circuit should be proportional to the linear dimension of the transistor. So, as the transistor were shrinking, so did the necessary and current, voltage and current. Power, so power is proportional to the area of the circuit. So it was very nice because it helped a lot the industry to develop the new generations of processors at that time. So there's a very nice sentence from Bob Caldwell that he said that Moore's law gives us more transistors, and Dennard scaling made them useful. Because if you had a CPU A with the number of transistors as equal to X and the power equal to Y, in the next generation or 2 years later, we have the CPU B with the same area, but with the double number of transistors, but with the same power, because the power is proportional to the integrated area of the circuit. Why? Because, as I said before, as the transistors are smaller, also are smaller the voltage and the current necessary to work the transistors. So we had the device miniaturization that drove the development of the first processors. So in the 8080 from Intel, one of the first processors from Intel, the second one actually, the transistor, the channel had a 10 micron size. The 8080, it was 3 micron in size, so 3 times smaller than this one. In the 286, it was half the size of this one. So at that time, as the transistors are smaller, and we know that the power in the same area are the same, so the number of the transistors were increased, the performance of the single core were increasing, and also were increasing the performance efficiency. So it was a very nice moment for the development of computer, because the software, the architecture, the implementation, the device could be developed independent from one to other. So the guys who were caring about software, they were not caring about the device because they already know that the next generation will run the same programs faster and with less energy. So it was a very good moment for the development of computer. However, some years later, Dennard scale failed. So Dennard is smiling here in this picture, and he's not smiled a lot anymore, just a small smile here, because he did not take sub-threshold leakage into account. What was the problem? Well, the transistor was shrinking, so they were getting smaller, 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 and it reached a size that the isolator barrier between the semiconductor and the metal gate was so thin that the tuner current increased a lot, and the transistor started to fail. So to solve this problem, we could not reduce the threshold voltage anymore. So we reduced the size of the transistor, but we could not reduce the power anymore. This was one big problem for the industry and for the humankind who became dependent of the computers. So the new processors, the new generations of processors, as that one said, we can see here, we still see that the size of the transistors are getting smaller, smaller. It's still getting smaller, smaller, smaller. But now, as the number of transistors still increasing and the performance is still increasing, the power efficiency is not increasing anymore. So it was in the beginning of this century. So 2003, 2004, we faced this power wall. So what was the solution? As we can see here, what's the difference between the processors in the previous slide and the processors here? If you observe, these processors here are multi-core. it was the escape. It was the solution for the problem. So what we have, this is another way to see Moore's law. What we see here is that the number of transistors is still increasing in the processors, but from 2005, the single thread performance it's not increasing anymore, such as the frequency, such as the power. How was the solution? As I said, the number of cores starts to increase. Why we did not have cores here before? Because it was not necessary. We know previously that the next generation of processors would be better than the actual one, because the number of transistors would increase with no increase in the power, but it was not the case anymore. And these machines today, they consume a huge amount of energy, and also they dissipate a lot of heat. So in order to keep it cooling, to keep it cool, to work properly, we can see that the big companies are putting their data warehouse in very, very cold place, such like in Sweden and Finland, because are places that are constantly cold. So they can use the weather to cool the machines. Also, we can see very interesting and crazy solutions like this one from 2016 from Microsoft, that they put a small data center under the sea to use the water of the sea to cool the processors. They still running these experiments today. They increase the number of let's say computer submarines to run in the cloud. It's very funny because it's used to run the cloud computers, but the cloud is under the sea. So maybe it's the reflex of the cloud. I don't know. They have to give another name for this cloud. It would be a strange thing if it's run well, and if it would be a solution. But I don't know if it's a good solution, because you have to see the environment around it, how it will behave with this system. Will it warm the water next to it? I don't know. Maybe some biologists will have to join the group to have the correct answers. Why you need to know about it? Why you need to know that the computer are changing? Because it's still changing. It's not the end of line. It's not because you have a cell phone that works very well that the computers are not improving, or that we don't need to improve the computers anymore. We still need to improve it. And more than it, we will not be the main users of computer anymore. Now, one of the main users of computer are the things and not the humans. So I put here pictures of very old things, but these very old things now has very cheap connections. They can talk with each other, and to do it, and it can talk with us as well. And to do it, it needs to process information. So they have to have computers embedded. So they start to become users. So for those who are interested in, there is a very nice paper in the communications of the ACM. It's a quite recent paper, 3 years ago, when they talk about the exponential loss of computer growth. And as we can see here, they say that the Moore's law is just one small component of an exponentially grow planetary computing ecosystem, because they say that the computer performance is increasing exponentially, thanks in part for the Moore's law, but the numbers of users are increasing exponentially, and not only human users, but as I said before, we have things users. and the data is increasing exponentially as well, because as we have more users, we have more users generating more information, and everything in computers is exponential. So it's a very nice paper that makes you think a lot about what you want to do in the future. So we put together the chip, the system, and the community. Everything is growing exponentially. And now, before I said that the computer was developed independently and each part, but now we are facing a different thing. We have what we call more Moore. We can, the software, the architecture, the implementation, the device, they are being developed together. So it's quite hard to do it separately. Of course, if you have the solution, the hardware, some guys can still work on software. But if you want to have the best software in the world, you have to work on hardware now. Let's see the machine learning example. Machine learning is a very good example. As I said before, I also have a background in machine learning. I use it in my PhD and apply it to solve some nanoscience problems. At that time, some years ago, 15 years ago, we only used CPUs. All our neural networks, for now, simple neural networks, the multilayer perceptron, for example, were running on CPUs. Wow, it was slow, but not so slow. At that time, we start to use GPUs to run our neural networks and other simulations because it was faster, but not so fast as they are today. More recently, the people start to see, well, if I develop, but these two guys here, the CPU and GPU, are general proposing computers, right? So the guys start to think, well, if I can develop my own hardware specifically to run, for example, my machine learning, I can get faster and faster solution. So the first thing, because it's more simple and it's cheaper, the guys start to use FPGA and to implement their machine learning solutions on FPGA. And even more recently, and especially for the big companies, they start to produce the all ASIC solutions specifically for machine learning. So now you have specific computers to run only the machine learning. And one of the most known example is the Tensor Processor Unit, the TPU from Google. And now they can create clusters of TPUs that are projected to run deep learning and other very hard machine learning solutions. So it's a good example to say that if you want to do the best software from the world, you need to know hardware because it's the only solution. And you have to care here because you have cooling problems, energy problems, and another problems that we are facing today. But where is the bottleneck? Can you do it forever? Can we always evolve? The answer is no. For example, the transistor evolution. We were seeing that the transistor is getting smaller and smaller, and when we change from the 32 nanometers to the 22 nanometers, we have a very revolutionary shape engineering change in the transistors. It stopped to be let's say bidimensional structure and start to be a three-dimensional structures with the 3 gates. More recently, we are in nodes like 14 and 10 nanometers, and more recently we are in the way to create like nanowire transistors to get close to 3.5 nanometers and something like that. In this graph here, we can see, it's another way to see the Moore's law. Here we see the size of the transistors along the years. So you have it's a log graph. So we have a linear here, linear points here, and we can see that along the years the transistors are getting smaller, smaller, and smaller. And then we got the barrier of 100 nanometers. This is a very important barrier because it's the where it starts the nano work. So do you know how many silicon atoms you have in a row in 100 nanometers? Someone have an idea about it? Okay, I have the answer here for you. The answer is 350 atoms in a row when we have 100 nanometers. So it's good. 315 atoms, it's quite a lot. I can create a crystal of silicon, which is my semiconductor, okay? But we want to go further. And if you go and we start to think about the transistors now, with 10 nanometers in the channel, we have 35 atoms. It's still good. It's hard to work in this size, but we have engineering solutions to solve the problems. But 35 atoms are not so much. And if you want to go further and further and further, when we reach 1 nanometer, we will have just 3 atoms. And forget it. Because with 3 atoms, we will not have a crystal. We will have what we call an atomic cluster of silicon. And the features of these structures is different. It's not a crystal anymore. And it will not work as you learn about semiconductor in the undergraduate school. So it will not work anymore. So we cannot go further. We cannot have transistors smaller, 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 and we are close to reach this stopping point. So that's why we are talking about nanocomputing. So when I say for someone that don't know what nanocomputing is, and he asked me, what is nanocomputing? And hey, imagine what is a nanocomputing. The first thing that comes to his mind, it's a computer in the nano size. It's not true. As I have just said for you, we cannot have an entire computer in the nano size. We are very hard to get transistors on that size. So it's not that. What is nanocomputer? So what is nanocomputer? It's a research and an application of nanostructures and nano device in order to create a new generation of computers. But here we are not talking about silicon nano device, or at least the traditional silicon transistors device. They are different. You can still work with silicon. I'll show you later, but not necessary to do transistors, okay? So this is what you can find in the literature as computer beyond silicon or beyond Moore. If you Google these terms, you will find a lot of nice papers and news about it. So let's go. One important thing to say here is that we will not give up from the traditional transistors that we have today. It works very well. We know how this works. It's very good to work with. The important thing that here is that silicon will not be replaced. It will get allies. So the idea is to have silicon together with other materials. Each material doing its best, their best, and then you can have a better machine with hybrid materials together. Okay. Here's very good reference for you. It's a very new reference. There is two special issues in the proceedings of IEEE. The first one was released last year. It's called Non-Silicon, Non-von Neumann Computing, Part 1. It was released last year. Here are the editors. Very nice guys, very smart scientists. And this month was released the second one, Non-Silicon, Non-von Neumann Computing, Part 2. So it's not only about beyond silicon, beyond Moore. They have another things in these issues, but it's a very nice issues with very smart papers that you can read and see what direction, which way we are driving our future computer and computer science, okay, and engineering as well. In these issues, you can find, for example, carbon nanotube transistors, which are quite similar to the silicon transistors, but they use carbon nanotubes in the channels and take the privilege and the good features of these very nice semiconductor materials. In some terms, semiconductor, and sometimes they are metal, so they are taking advantage of these properties. We can see a very nice paper about DNA computing and DNA memory. You can find some words in spectronics and so on. What I'm going to talk for you today, for the remainder of this talk, it's about some of the technologies that we are working at Nanocomp, at our lab here in Belo Horizonte, in UFMG. So I will talk about field-coupled nanocomputing, photonic crystal computers, and DNA computers. What they share together, none of these use electric current as the basic controlled physical entity to make the computer work. So let's go. The first one is field-coupled nanocomputing. This idea came from Craig Land in the beginning of the 1990 decade. And the first one was QCA, quantum dot cellular automata. What they do, as I said, it's a cell. They work with a cell with 4 dots. Imagine 4 simple dots here. Don't care about the physics now. And you can just imagine that inside this cell, you have 2 free electrons, and these electrons can be positioned in these dots. Because of the Coulomb repulsion, this electron will tend to be placed in opposite diagonals. So they have 2 possibilities. Or they are like this one here. I say that the black dots are where the electrons are. So we have 1 electron here and 1 electron here. And we can say that here, this one is binary 1. And if they are in the opposite diagonal, we can say that it's binary 0. So we are not working with quantum computer here or qubits. We are working with bits. Classical computer in a quantum structure. If I put 1 cell next to the other in a row, the position of the electrons in one cell will interact with the electrons in the other cells. They all will tend to have the same polarization, and you have a Y. Well, right? If I do some smart engineering with these small squares, I have more interesting gates. For example, a NOT gate. I have here a fan-out, because this cells and this cells is next to this one. So it's a fan-out. I put 1 here. And when I have the cells in diagonals with the other ones, they change their polarization, so they have a NOT gate. There is a very nice and smart gate here for this technology, QCA. That is the majority gate. This, as the name, they have 3 inputs, input 1, input 2, and input 3. And the output will be the majority of the inputs. So if we can see here, input 1 and input 3 are with polarization 1 or logic 1, and input 2 polarization -1, which is logic 0. And the cells, the electrons here will feel the interaction between these two. One is stronger than this one. We can have a repulsion here, but it's better than have a repulsion here and a repulsion here. So it takes the majority of the polarization and pass to this output cell here. If we fix one cell, for example, if I fix input 2, I can create an AND gate with input 1 and input 3 as the inputs, because I will have 1 in the input only if these two are equal to 1. And I put this in 1, I will have an OR gate. So with an OR gate, an AND gate, an AND gate, an OR gate, NOR, a NOT gate, and RIDES, I can do what I want. So here are some design we have developed in the past. So we proposed some years ago a nano router with QCA. We created a clock scheme. I will not talk about this today here, but it's a very interesting way to control the polarization of the cell. So it was a very smart solution from one of my master's students. And more recently, we start to work with another field coupled nanocomputer, which is called NML, nanomagnetic logic. Instead of working with the quantum dots, we start to work with magnetic structures. If we have elongated nanomagnetic structure like this one, it cannot be very big one and cannot be very small, something like 50 for 100 nanometers in size. All the spins inside this magnetic will tend to have to point to the same size, to the same directions. And this is the long axis here, what we call z-axis. So if they are all point up, we say that's logic 1. If they are all point down, we say logic 0. If you put one next to the other in this situation here, what we call ferromagnetic interaction, they will say you have the same magnetization. If I put next to the other in the short axis like here, they will have opposite magnetization. You can see here that the tonal energy, this dots one here, are smaller here than here. So they tend to invert their polarization. So here it's a work from the guys from University of Notre Dame. It's a microscopy of a nanomagnetic logic circuit implemented with permalloy. And they did all the calculations. And here in the arrows, we can see a magnetic field, a magnetic force microscope, and we can see that it works very well with just a small single error here. In a recent work, we showed that if we cut, we make some cut structures, we can make stronger coupling between these structures. This was a very nice work. It was the cover of IEEE Transactional Magnetics 3 years ago. And today we have a simulator. It's available. You can send me an email. I can give you the link to get the simulator. It's called NML Sim. This is one of the picture exporter. It's a full adder that we implement there. And here we're working with the controlled clock zones controlling the information process. So here's this is the interface of the simulator, and we can see all the simulations and the animations of your circuits. So just send me an email and you can use it. Another very nice now change. You can see here that you have, if you pay attention, we did control the current, electric current. There is no electric current, just field couple close to each other. Here it's a very nice, another very nice structure, what you call photonic crystal. We have materials with periodic different materials with different the electric constant. So you can have it in 1 dimension, 2 dimensions, and 3 dimensions. This is what gives the colors to the wings of the butterfly, for example. The beetle as well get colors because of this these structures, these physical structures in their wings. We can create our photonic crystal. Here we are working with two-dimensional photonic crystal like this one. And this two-dimensional photonic crystal could be rods like these ones, spaced, very, very periodic spaced rods. Or I can have a silicon substrate, for example, and I create holes in this silicon substrate. So this became a photonic crystal. And as a electronic semiconductor, it gets a band gap. But in this case, it's a photonic band gap. So if I take advantage of this photonic band gap, if I take a light with the frequency of the prohibited frequency inside the gap, and I throw this light to the crystal, it will be reflected like this one. It will achieve the crystal and it will be reflected. That's what happened in the butterfly, in the wing of the butterfly. But I can create defects. If I took some of these rods away and I still with the semiconductor here, I can throw the light in this structure, and the light will go in this way. This is what we call wave guide. It's a guide for the wave that I'm throwing there. Then I can play here, and if I play with if you remember your optics lessons in the physics course, we can take advantage of the constructive and destructive interference. If they have the same phase, or a phase separated by this constant here, we have a constructive effect, and I put light here, I have a strong light in the output. If I change the phase, like this here, I put light here, and I have a destructive interference here, and the light will be destroyed here. So we took advantage of this, and we proposed some gates. This one was a majority gate, as in the field couple nanocomputing one. And here with 0, 0, 1 input and a 0 in the output, and 0, 1, 1 with a 1 in the output. We have proposed another gate. This is a gate that will be present now in the Euromicro Conference on Digital Design, Digital System Designs, the DSD, next week, actually. So we have two inputs here, source A and source B, and these structures, if I just play with these holes here in the junctions, and I have a source F here that is always on. If I play with these holes here, I can create a NAND gate or a NOR gate with the same structures. But I have a problem here. If you see here my NAND gate, the logic one, for example, the NAND 0, 1 equal 1, the output is half the input of the values of the input, which is, it's not very good, because how can we cascade these gates? This is the biggest problem now with photonic crystal logic gates. So we have a lot of papers from 2013 to 2014 from now to now, proposing a lot of photonic gates structures, but none of them can be cascaded to create systems. And we want to create circuits and then systems. So I have a PhD student that focused to solve this problem. So this paper is under review at the Opti Letters. So we took a structure that were already tested in the literature, not for logic, but it's made with aluminum, gallium arsenide, and gallium arsenide. And we create, inspired in the N-type transistor and the P-type transistor, we create an N-type switch and a P-type switch with photonic crystal. So In the N-type switch, we have an input and a control, and you have an output and a drain. The output will be 1 if the control is on and the input is 1. Otherwise, it will be 0. Here's the truth table. And the P-type switch, the output will be 1 if the control is off and the input is 1. So it works like a P-type transistors. So this is a very nice work because we can create complementary photonic crystals integrated logic devices. So I expect to show you in a very short time some circuits that we have already simulated. And now we are working with a collaborator to synthesize these circuits, physically synthesize. Another thing that we are working now, it's with DNA computing. So here we can see an example of an AND gate. We have 2 inputs, A and B, and the output will be C. So C will be released as a DNA molecule only if you have A and B at the same time. Then you have C. This is a very interesting way to do logic circuits, but it's a very hard one because, as you can see, the gate is destroyed. Once you use the gate is destroyed, and you do not have wire to connect one gate to another. So we will have to use molecules, DNA molecules, to connect one gate to another. We are working, and we have some very nice results and recently with our work. We developed a framework in R language, what we call DNA R, that you can use to simulate it, and you cannot export for a very good tool from Microsoft, Visual DSD. So we can use DNA R that are much simple than the Visual DSD, and then you can export to Visual DSD to do another simulations. So here we are doing some, for example, some digital logic simulations. Here are majority gates that we have proposed. And this DNAR work is under review in the ACS Synthetic Biology journal. And to finish this presentation, I showed you 3 possibilities of working to do computer systems, different computer systems that do not use electronic current and can be very interesting for different kinds of applications. For example, field coupled nanocomputer is not fast, but it has a very low power and has a very good throughput. So it can be very nice to use in IoT, for example, IoT systems. Photonic crystal computers can be used to connect with the network because you can have a logic structure connect to the network. It's very good. You can put together the communication and the processing. The same thing here in the field coupled nanocomputer, especially the nanomagnetic logic, you can put together the memory and the logic process in the same chip and together. System chip logic in memory, for example, and DNA, of course, can interface with the biological system. We can create a logic system that can be input, can be inserted, for example, in in vivo structure. We are far from that, but we hope that we can do it in the future. And the very, very, very nice thing that they share together is that they are all very low energy structures, very low power required. So we can achieve the fundamental physical level of energy. So talking about this, we have a lot of works on reversible computing that we can achieve with this technology. So we have a very nice, interesting papers that you can see and do what we have done. And if you are interested to cooperate, we are always open to cooperate in any of these topics. So that's my thought for today. And once again, I want to thank Ricardo for the invitation, and I'm open for questions. Thank you.
Thank you very much, Omar. So we have some questions now. The first one is by João Carlos Nunes Bittencourt. So congratulations for the very good presentation. Will nanocomputing converge with quantum computing in the future?
It's a good question. I think that quantum computing already is a kind of nanocomputing. If you think calmly, you can say that you have to use nano devices to create the quantum computer. So they are already an application of nanocomputing. But as we know, quantum computers are not good for everything. And classical computers are better for other things. Maybe in the future we can put it to work together. It will be a very interesting thing to do. It's a good question. Good question for the future.
So I have a question by Professor Fábio Ramos from Unipampa. Thanks for the nice talk, Omar. In your opinion, how far we are from using in common digital design the approach presented instead of, for instance, a CMOS standard cell PDK?
Another very good question. It's difficult to answer because I have to do forecast here. Well, I think that the first nano structures that will be used in the industry will be the carbon nanotubes. It's still working with electronic current. They will be the first one. I think they are very close to get the market in the next decade. But the other technologies, I don't know yet. It's quite hard to answer these questions because you don't know if all of them will survive. I showed some of them for you today, but there are another possibilities. What I think in the future is that we will have, as I said in the middle of the talk, a mixture of hybrid technologies, and it will depend on the application. But it's difficult to answer this question. Maybe I'm quitting here the right answer, but I don't have it. Sorry.
Just a comment about about the physical design of carbon nanotubes circuits. This will be the subject of a talk by Aida Trodi Sanial in the next, the 10th edition of the CASS Rio Grande do Sul workshop, November 11 to 13. So you are all invited to attend this talk about the carbon nanotubes. So another talk here now is from Professor Palomino. So he's saying the same way of Fábio Ramos, how long will nanocomputing be on a new electronic device?
I think the answer is the same. It's difficult to know. Really, it's difficult to know because it's quite a change in the way that the industry is normally working. So I don't know how to answer this question. It's difficult. I think it will possibly in small solutions, we will have it in the next decade. Probably in small solutions for IoT nodes, something like that. Maybe you can have some things because you can use the same structure for be the sensor and the logic processor at the same time. So maybe it'll be the first applications.
Okay, I can see that Clovis is typing a question, but before that, I have another one in CMOS circuits nowadays. Bulk CMOS, FinFET, FDSOI, all of them. There is always a question about using small gates or large gates doing more complex functions. What we can see is that using large gates, we have a nice reduction in the transistor count. That also means a reduction in static power. So how is this dichotomy in nano computing about using small gates, logic gates, or bigger logic gates?
It depends on the technology, Ricardo, because, for example, the photonic crystals, they will have large gates because the structure is not small. The holes are small, but they cannot be so small. They are in the order of some hundreds, 200, 300 nanometers diameters of each hole. So the structure is quite large. So the gate will be large, but as they have low power, they will be a very good interface with the connections, the network, with the network. So this is the advantage. But in field coupled nanocomputer, on the other side, there is a group in Alberta University in Canada that they have just developed a silicon QCA that they using dangling bonds. So they use just a few number of atoms to create a cell. So they will have very, very small gates. And it will be much faster than the previous QCA solutions. So I think it depends on the application, depends on the materials. For example, this atomic QCA will be very small gates, and the photonic crystal will be very large gates. And they have different applications where we can use them.
Okay, so a question by Clovis Higgenbaum. Could you tell what would be the effects of great variations of temperatures on these three types of computing devices? So field-coupled nanocomputing circuits, photonic crystal computers, and DNA computing. They should work on very low temperatures?
Good question. The traditional QCA, yes, they have to small, very, very small temperature. Nanomagnetic logic, it's not necessary. It works on room temperature, but you have to take care. Your wire cannot be much longer because there are thermal fluctuations that chip the bit, and it will not work correctly. The DNA, it depends on the application, but it can work on room temperature. You have the DNA inside our body, so it's not a problem. And the photonic crystal, depends on the material. If you are working with silicon, you can have higher temperature. But if you are working with gallium arsenide, for example, you need very, very low temperature. It depends on the material.
Okay, so I have no more questions here. So thank you very much, Omar, for this very nice talk in a very interesting subject.